Welcome. Let's continue the chapter sound. Today, let's focus on propagation of sound, the second part. As you already know, this chapter has six topics. Okay. Today, let's focus on the second part, the propagation of sound. Have you ever wondered how that catchy tune reaches your ears, or how whales communicate across vast oceans? The secret lies in vibrations and sound transmission through mediums. Look at the images for some of the sources of sound. Remember the ripples you create when dropping a pebble in water or you yourself jumped into the water? Sound travels in a similar way, not through particles zipping across the distance, but as a disturbance that ripples through a medium. Imagine pushing a domino in a line. One domino falls, pushing the next, and the effect continues down the line. Similarly, when a vibrating object like a tuning fork displaces air molecules, these molecules bump into their neighbors, creating a chain of reaction of displacements. These displacements don't involve the molecules traveling along the distance, but rather vibrating around their original positions. Disturbance itself, however, moves forward carrying the sound energy. Okay, so it's very clear now. So the molecules will not move the long distances. Molecules only vibrate around their original positions. The disturbances moves forward carrying the sound energy. This rippling disturbance called wave is what we experience as sound. Sound waves are classified as mechanical waves because they require a medium to propagate. Air can be a medium, water can be a medium, there are so many other solid objects can be a medium. These waves are characterized by specific properties like wavelength, frequency, amplitude, which determine the pitch, loudness, and other characteristics of the sound we hear. Okay, now let's deep dive into air show. When vibrating object moves forward, okay, for example, think of a prong. When a vibrating object moves forward, assume moving to the right side, it pushes air molecules tightly together, creating a compression of high pressure. Okay, from here you see this prong moves right side, these air molecules are pushed towards right side. It means in this region the density of air molecules is higher, it's a compressed region. Okay, the pressure is higher. You can also imagine like you're squeezing a balloon. Okay, conversely, when an object moves back, in this case the prong moves back, for example, it leaves a gap in the molecules. In this case, see, in this there's a gap here, right? It leaves a gap in between the molecules, forming a rarefaction of low pressure. And what does that mean? So you can also imagine, like, you press the balloon and removed your grip on the balloon. What does that happen? The pressure got now reduced. Similarly, the prong is moved to the left side. At the neighborhood of the prong, we have a rarefaction, because there the number of molecules is lesser. The density of molecules is lesser. So we call it as rarefaction. And then what is this pressure tango? See, pressure is changing. You know increasing, decreasing, increasing, decreasing, right? This back and forth motion create the what is back and forth motion of the object, in this case prong, the prong. Okay, this back and forth motion creates a series of compressions and rarefactions that travel through the air like a wave. Okay, remember the air molecules themselves don't travel along the distances, but the pressure variations do. Air molecules don't travel along the distance, remember this, but what it travels is the pressure variations. Now, just to explain it, in a different way, think of a slinky being stretched and squeezed. The slinky itself stays in the place, right? But the waves of compression and rarefaction move along its length. Will try to visualize later. Okay, what does it mean? Higher pressure in compressions means more molecules packed in a smaller space. For example, more molecules packed in a smaller space. It means higher pressure or higher density of the molecules. In rarefactions, the opposite happens. Fewer molecules spread out in a larger volume. See, this volume is larger, but fewer molecules. It means the density of molecules is lesser, or pressure is more in this region. Pressure is less in that region. Okay, so you can also visualize sound propagation as a wave of varying density within the medium. You think it's now clear, right? You can visualize the sound propagation as a wave of varying density within the medium. What are the key takeaway then? So compressions and rarefactions are the building blocks of sound waves in the air. Understanding this pressure dance is crucial to grasping how sound travels and reaches our ears. With this, you should be able to answer these questions. First question: how does the sound produced by a vibrating object in a medium reach your ear? How does that sound reach your ear? You should be able to answer this question. Explain how sound is produced by your school bell. Third one: why are sound waves called mechanical waves? Why not they're called as some electromagnetic or some other waves? Why they're called as mechanical waves? Suppose, the fourth question: suppose you and your friends are on the moon. Will you be able to hear any sound produced by your friend? Think and answer these questions. Okay, refer to the previous video uh, again to answer this, understand and answer this. See, propagation of sound was the second topic I said, right? In that, you learnt the first subtopic. Next, go for the second subtopic, which and understand why sound waves are longitudinal waves. Now, let's get wavy. Grab your trusty slinky and a curious friend. Remember, we are doing activity. This activity will have us unleashing the power of waves. You know the slinky, right? You would have played definitely. Now what do you need to do? What are the activities you are supposed to do? You need to do stretch and push and observe. Simple. Stretch, push and observe. So hold one end of the slinky with your friend holding the other. Gently stretch the slinky out, creating a straight line. Just imagine, you're just stretching it to make it a straight line. Give the slinky a quick sharp push towards your friend. It means you're pushing it inside. Okay, the right side mark. This way you're doing. Up. Then what happens? Observe then. What happens to the slinky after you push? Does it stay still and travel in one direction, or something else entirely it behaves? What do you notice? If you move your hand pushing and pulling the slinky alternately, what will you observe? If you see slinky is there, you push and pull, what happens? Did you observe? Just observe that part. If you mark a dot, okay, assume you mark a dot somewhere here. Here, if you mark a dot on the slinky, you will observe that a dot on the slinky will move back and forth parallel to the direction of propagation of disturbance. What is the direction of propagation of disturbance? This is the way, right? This is the direction of propagation of disturbance when you are moving, assume you are pushing it, right? So this dot is moved this way, left and right, left and right, left and right. It is parallel to the direction of propagation of disturbance. Clear? Now let's go further and decode the slinky and understand the sound waves. Again, let's take we already took the prong and we created vibrations, right? And that vibrations created the sound, and and that sound is created by the disturbance in the air molecule in the air. Now let's go with the slinky way. Okay. uh, so slinky, imagine a slinky. It coils a wave frozen in time. Remember, it's a wave frozen in time. Think this way. Okay. What is it? See, I mean, think this way now. It's frozen now. See this portion and this portion. There are two compression zones here. You can also experiment in your house, with a slinky. The compression zone is a coil where coils bunch up like air molecules crammed together in a sound wave. Like, here air molecules are crammed together in sound wave, right? Here also, observe this region. Okay, the coils bunch up. Okay, and this is called as compression zone. It's compressed, right? Similarly, rarefaction zone, where coils spread apart. See in this region, the coils are spread apart like air molecules stretched outside the wave. See in this region, air molecules are stretched apart. Okay, so we could observe the compression and rarefaction in both the cases. One with the prong, other with the slinky. Now tuning fork and slinky both. So let's connect the dots now. Sound travels through air as a series of compressions and rarefactions. See, what is the similarity between both the cases? In both the cases, we see compressions and rarefactions. It means when we connect the dots, it becomes sound travels through air as series of these compressions and rarefactions. The slinky's behavior mirrors how sound waves move through a medium. Sound waves are longitudinal, meaning particles vibrate parallel to the wave's direction. There's something like a transverse, we'll see it later. But here what happens, the particles vibrate in parallel, okay, to the wave's direction. Wave's direction is this way and particles move this way, left and right, okay. This back and forth oscillation, like the slinky coils, carries the sound energy forward. Let's continue further. Let's go beyond slinky now. Okay. So not all waves are slinky, remember. No, see, we created some waves, right, using slinky. Okay, that remember, not all the waves are like the slinky. Meet the transverse waves, where particles wiggle sideways, not back and forth. See, not left and right, up and down. Wiggle sideways, not back and forth. Imagine the wiggle, Picture a jump rope. You might have, you could, this one, right? This one. So you definitely would have, played this rope, right? Swinging rope game, right? Skipping. Picture a rope, jump rope swinging up and down as it travels. That's a transverse wave. See, this swing goes up, come down, goes up, come down. That's a transverse waves. Okay. Water. Similarly, we have a water, ripples. Ripples on a pond or a vibrating guitar string. See these ripples? This is a vibrating guitar string. They also are examples of transverse waves, where particles move, vibrate up and down. Means perpendicular to the direction of movement, direction of disturbance, direction of sound. Even the light is a transverse wave, remember. But remember, it doesn't need a medium to wiggle through a space. So light is a transverse wave, but it's not a mechanical wave. It doesn't need a medium to for it to move forward. So transverse waves differ from slinky longitudinal waves. Particles move perpendicular to the wave's direction. Remember, in the transverse waves, particles move perpendicular, up and down, up and down. Okay. Examples of around are water ripple. Water ripples are perfect examples of the transverse waves. Vibrating strings, for example guitar. Even the light are all transverse waves. Light is unique in its medium-less travel. It doesn't need a medium for light to travel. Okay, though it's a transverse wave. Okay, making the special kind of a transverse wave. Let's continue further. Sound propagates in the medium as a series of compressions and rarefactions. We learned it. Series of compressions and rarefactions. In the longitudinal waves, the individual particles of the medium, for example air molecules, move in a direction parallel to the direction of propagation of the disturbance. The particles do not move from one place to another, but they simply oscillate back and forth about their position of rest. This is exactly how a sound wave propagates. Hence, sound waves are longitudinal waves. Okay. In a transverse wave, particles do not oscillate. Okay, along the direction of wave propagation, but still oscillate up and down about their mean position as the wave travels. Remember this example of the here, for example here, right? The particles move up and down, up and down, up and down. Okay, whereas here the particles move left and right, left and right. Increase the density, reduce the density, increase the density, reduce the density, like up and down, right? Here up and down, here left and right, right? Remember, longitudinal transverse. Thus, a transverse wave is the one in which the individual particles of the medium move about their mean positions. Of course, mean position is the center position is the mean position. Okay, about their mean position. Okay, in a direction perpendicular to the direction of wave propagation. See, this is the direction of wave propagation, reaching your eye. This is reaching your eye, right? Here, perpendicular, up and down. Okay, remember. When we drop a pebble in a pond, the waves you see on the water surface is an example of transverse wave. You can see the ripples up and down, up and down. Example. So water ripples, ripple on the water are example of transverse wave, though and they are mechanical waves, remember. Light is a transverse wave, but for light, the oscillations are not for the medium particles or their pressure or density. It's not a mechanical wave. Light is not a mechanical wave. It doesn't need a medium. So the question of particles movement doesn't appear here. Again, summarizing it. Okay. Sound waves are longitudinal waves. Okay. We know it already. Now we complete one more subtopic. The sound waves are we got a clarity. Sound waves are longitudinal waves. Sound waves are mechanical waves. We got a clarity, and we also learned the other kind of a wave, which is transverse waves. Light is an example. The water waves, water ripples are an example. Suppose another example, right? Now let's go to the next topic. Let's understand characteristics of this sound wave.